Consider waking up some morning and planning to spend a day out. To pack the right clothing, it might be very helpful to know the maximum daytime temperature. Indeed, in the morning we can observe only the minimum daytime temperature. We can model this problem as a machine learning problem where data points represent individual days whose feature is the minimum temperature that can be observed in the morning. The label of a data point is the maximum daytime temperature that we cannot observe yet in the morning, but would like to predict. A basic machine learning approach to this temperature forecasting could be to collect historic weather recordings from the Finnish Meteorological Institute, which operates weather stations all over Finland. These recordings are freely available for download from the webpage of the Finnish Meteorological Institute. After downloading the weather recordings, we can learn a hypothesis out of a model by minimizing the empirical risk incurred on the weather recordings. The learned hypothesis then predicts the maximum daytime temperature from the minimum temperature observed in the morning. Note that the weather recordings consist of a collection of local datasets. Indeed, the Finnish weather stations generate local datasets all over Finland. Federated learning methods train separate machine learning models for each local dataset in a distributed manner. These methods avoid the collection of raw local data at a central computer or server. Using individual models for each local dataset is appealing computationally and statistically. Indeed, federated learning methods distribute the computational burden of model training using computing resources available at the local datasets. For example, a weather station typically also includes a computing device. Statistically, using separate models for each local dataset allows to learn different hypotheses for heterogeneous local datasets with different statistical properties. A principled approach to federated learning is via an empirical graph. The nodes of the empirical graph represent local datasets, such as the weather recordings at different weather stations. Besides its local dataset, each node also carries a local model, from which we want to learn a tailored hypothesis for the node. We connect two nodes by an undirected edge or link if they carry local datasets with similar statistical properties. A positive edge weight quantifies the level of similarity. We can determine the statistical similarities between local datasets in different ways. In some applications, we can use domain knowledge, such as properties of the data generation process, to determine these similarities. Moreover, we can use established statistical tests to determine if two datasets have the same probability distribution. Such a test could compare the sample mean and covariance matrices computed for each local dataset. We can use the empirical graph to regularize the training of the local models by adding a penalty term to the sum of local loss functions. This penalty term is a scaled measure for the variation of hypotheses across edges in the empirical graph. The total variation is the sum of the distances between the hypotheses at nodes that are connected by an edge. Each of these distances is weighted by the corresponding edge weight. We can obtain different instances of total variation from various distance measures. Total variation minimization favors hypotheses that do not vary too much over clusters. where a cluster is a subset of densely connected nodes in the empirical graph. The regularization parameter lambda controls the clusteredness of the learned hypothesis. Using small values for the regularization parameter allows each node to learn a tailored or personalized hypothesis. Increasing the value of lambda results in clustered federated learning, which pools the local datasets in well-connected subsets or clusters of nodes. Finally, making lambda sufficiently large enforces the learned hypothesis to not change across any edge. If the empirical graph is connected, this implies that all nodes learn the same hypothesis. Note that even if all nodes learn a common hypothesis, the learning process is distributed and does not involve sharing raw data, but only model parameter updates. One popular implementation of federated learning of a common hypothesis is known as federated averaging.